Hello and welcome to another video. This time we're going to be looking at how we can get analog signals into our Agon computer. We're going to be using a module based on the ADS1115 chip. This provides 4 analog inputs and these can be read on the I2c bus. The connections on the board are really easy to see, with the inputs at one end and the I2c connections at the other. In the middle there's an extra pin which you can use for changing the address. In today's example code, I've wired up a simple potentiometer to one of the analog inputs. In this diagram we can see that the connections go off to the Agon for the I2c signals. One side of the resistor is connected to ground and the other to plus 3.3 volts, with the centre pin connected to the analog input. If we look at the code for this project, we can see that we have some initial default values set up, the I2c bus, and then various attributes for this module. There's an input channel, and this relates to the current one we're using. But I've also set up some constants if we want to change those during our code. There's a value for what's called the gain, and this is really the range of values that we might get as a result. There's a default for the sample rate, whether the comparator is turned on or off, a command we're going to send to the configuration register, and there's a conversion register memory address which we will call when we want to retrieve data. So once we start the usual putting a display on the screen routine, hiding the cursor and so on, the next thing we'll do is set the ADS channel to be the one we want to use, in this case 0, and we'll store that for later. We'll then send the configuration, and this tells the unit how we want to read data and through which port we want to read it. In this example we're only using one port, so once we've set it up once we don't need to change it. But if you were to add multiple ports that you were going to read, you'd need to change this before every reading. And so our main loop obviously checks whether we want to press the escape key. We have a little delay so it doesn't run too fast, and then we keep reading from the device, and when we get the results we display it on the screen. So let's look at the configuration. The first thing is we define where we're going to store the data to send in terms of configuration. We're then going to send 3 bytes. The first byte is simply a command which says we want to write to the configuration register. The second and third byte make up all the configuration details that we need to send. When it comes to the second byte, bit 15 we're not going to set with anything, we'll leave that at 0, and the same with bit 8. Bits 12 to 14 set the input channel we're going to use, and bits 9 to 11 determine the programmable gain. This is really the range of results that we're going to get. Again, with the third byte there are only some sections we need to set: the sample rate and the comparator, and we've set these up defaults at the start, and these don't need to be changed from what's set here. We then send those 3 bytes to the module, and the configuration should be set up. So next, on to reading the results, we send the 1 byte AD conversion register which we've set up before, which is actually 0, and it just says we want to read from memory address 0. We wait a brief moment first, and then we read 2 bytes into our buffer from the module. Those 2 bytes will be a 16-bit value of the analog reading. When it comes to displaying the results, this is really simple. We're using our debug routine and reading the 2 bytes that are stored in our buffer. If we run the code, we can see what happens. On our display on the Agon, we have the most significant byte and the least significant byte from the analog reading on port 0. If I turn the dial, you can see that the most significant byte changes reasonably well, and the least significant byte is changing extremely quickly. As I turn it all the way, the maximum value we're getting is 65 as the most significant byte. And all the other way we go down to 0. So why do we get a result only up to 65? If we take a look at the gain value, that is the range of results that we can get, we've set the gain value to be up to 4.1 volts. That gives us a scale from 0 to 65 hexadecimal. If we set it for a scale of 6.1 volts, then we would only get up to 43 in hexadecimal. If we set the scale to 2 volts, then we've got a maximum range of 0 to 7F, but that maximum will happen at about 2/3 of the turn of the dial. Similarly, if we set the scale to 1 volt, we would max out at about 1/3 of the turn. So the best compromise for us seems to be setting at 4.1 volts, where we get a full turn and get a reasonable range of values. The reason we're not getting 0 to FF is that we're operating at 3.3 volts. So we've got to pick the closest one which is suitable for our needs, which gives us the full range of the potentiometer dial. Even with the full value of up to 7F, it's not FF like we might expect. That's because one of the bits on the 16-bit data is actually reserved for negative numbers. In this example, we're only using positive numbers because we're going from 0 to plus 3.3 volts. Negative numbers are only used on this module if you're comparing two different voltages where one might actually be lower than the other. So do you have an application for an analog input on your Agon? Maybe a dial for a game controller. Maybe there are other analog devices you might want to plug in, such as this light sensor.